Good afternoon, good morning, good evening. Thank you, all you that are joining us for this next CASS talk today. So today we have Professor Roberto Gómez-García from University. He is also a distinguished lecturer of IEEE Secret Site. And today we have also the pleasure to have here Professor Sandro Ferreira as the session chair. So thank you, Sandro and Robert. But today we are here for the presentation of Professor Roberto Gómez-García from University of Alcalá, Spain. And I give the floor to Professor Sandro Ferreira, that will be the session chair today. So Sandro, the floor is with you.
Thanks, Professor Ricardo. It is a pleasure to be here with this very hot topic, right? Since we are starting our 5G approach and 6G approach everywhere in the world, so DRF filtering is one of the main parts in that, right? To make sure it is feasible, right? And we have Professor Roberto Gómez-García that will bring us this interesting talk. Professor, please, you are welcome to present. It will be a pleasure to have you here.
Thank you very much, Sandro and Professor Reis, for this nice invitation. It is my pleasure to be here today, having the opportunity to give this talk. So the title of this talk is Reconfigure the World, Adaptive Transfer Function and Multiband Radio Frequency Filtering Devices for Emerging Wireless Systems. And my name is Roberto Gómez-García. I am an associate professor from the University of Alcalá at Madrid, Spain. Alcalá de Henares is a city that is famous because it's the city where the famous writer Miguel de Cervantes was born, that probably most of you know very well as the author of the very famous book of Don Quixote. But today we will not focus on literature, but on telecommunication, wireless things. So basically the outline of this presentation is the one that we can see on the slide. I will start with a brief introduction in which I will try to motivate the purpose of this talk, that basically is to enter into the design of multifunctional and reconfigurable filtering components as the key or the essential devices for next generation wireless systems. Then this talk will be split into two parts. In the first one, we will focus on the topic of multifunctional filtering components, so we will understand what we mean by multifunctional. After that, we will enter in the second part that is devoted to new filtering devices with very advanced features in terms of reconfiguration of the transfer function. And then we will conclude with a summary of the most important remarks of this talk. Well, we all know that modern trends in the field of wireless communications and radio frequency sensing applications is that we want our terminal to be able to support more applications and functionalities. And this can be illustrated here in this draw that we have here. But of course, if we take a look inside the terminals that are able to support all these services, we can find that indeed, in order to be able to support all the services and to provide all the functionalities that they are expected, we need to make our device very complex. So for example, in the right-hand side of the slide, we can see what will be today obsolete, but what will be the circuit block diagram of a multifunctional transceiver for 2G, 3G, LTE from Fujitsu. So today we have even more advanced. But we can see that indeed, in order our transceiver to be able to provide all the functionalities that we expect, we need to duplicate the circuits. For example, if we take a look to the number of filtering units that we need in order to acquire all the signals from each of the service that we want our terminal to support, we can see that we have a total of 20 filters. That is a lot. And the same applies to other kind of devices, for example, amplifiers, matching networks, and so on. So this means that if we follow this kind of approach to increase the number of services that our terminal is able to provide, means that we need to increase a lot the complexity and also the size. And also we need to consider that most of these radio frequency devices will be active. That means that in order they can operate, we need to bias them. So this means that if we need to increase the number of circuits, we will increase also the power consumption and the cost. So basically, we can understand that increasing the number of circuits to support the number of services that we want for our device is not a very efficient approach. So a more efficient approach will be to replace, for example, all these filtering units by a single filtering device that can be reconfigured in the transfer function, so that the same device can provide the acquisition for all the signals that our terminal will want to support. And of course, another way to reduce hardware complexity is to combine together the different radio frequency functionalities that we have for the different circuits. For example, instead of having amplifiers, filters, matching networks, we can think in new multifunctional devices that can combine in a single circuit all the functionalities. For example, a filtering amplifier, a filtering matching network, and so on. And this is one trend that will be adopted in the future, trying to replace all these monofunctional static devices by a single multifunctional reconfigurable device that can provide all the functionalities that we want. But another problem that we have, because what we have explained is for the acquisition of the signals that we want for our terminal. But another problem that we have is that today the electromagnetic spectrum is very crowded because there is a large amount of wireless systems that are exploiting the radio frequency spectrum. And this means that our system will be exposed to the interference coming from other systems. And in addition to that, we can also have interference, for example, in the receiver that are generated by the transmitter of our system. In summary, the situation is that we need very efficient radio frequency interference protection mechanisms in order to assure the robust operation of our systems. And this can be done at the signal processing level, but it's more efficient to do that at the hardware level, mainly by means of filtering, because if we are able to reject the interference signals directly from the radio frequency front end, we can get rid of the problems that can be produced. So here we can see what will be two different scenarios about a single or a conventional wideband receiver that is exposed to the desired signal that we want our system to acquire and some interference signals. An easy situation to handle will be that in which all the interference signals are far away from the desired signal. So in that case, basically, the only thing that we need is to have a radio frequency filter that is quite selective in order to provide enough rejection in the out-of-band region for the signals that we don't want to acquire, the interference. But another situation that can happen is that some of the interference can appear very close to the frequency range of the desired signal. In that case, we need to make the transfer function of the radio frequency filter more complex. So basically, we can see that in order to get rid of this interference that is allocated very close to the desired signal, we need our filter to produce or to introduce some kind of notch inside the operational bandwidth. So what I want to emphasize here is that we need filters with more complex transfer function in order to handle all the interference scenarios that can appear. And the situation gets even more complicated if we think that in principle, we don't know where this interference can appear. So basically, we want these notches that we can create and our filter to be reconfigurable to handle any kind of dynamic scenario in terms of interference. So basically, from now, I will introduce the two topics of this talk, that is multifunctional filtering components and reconfigurable filtering components in order to provide all the needed functionalities for next generation wireless systems. So what we understand by a multifunctional device? So basically, we can say that if we think in multifunctional filters, a multifunctional filtering component will be a device that, in addition to provide the conventional filtering capability, can also provide some other radio frequency analog processing functionalities. And what benefits we can get from this multifunctional philosophy when compared to the traditional approach in which what we do is to cascade together several monofunctional blocks? The first one is that we will have more compact designs because some of the circuit elements can be reduced by the different functionalities. Also, by means of the co-synthesis in the same device of the different functionalities, we can also optimize the performance. And another important advantage that we get is that we can reduce the insertion loss. And the insertion loss is an important parameter because at the end it's related with the sensitivity of the receiver. That is the capability to receive low power signals. And in the literature today, we can see that in the last few years, a large number of multifunctional components has been proposed. For example, filtering power dividers, filtering amplifiers, filtering transformers, balance filters, and so on. For example, filtering antennas, filtering phase shifters. So basically, it's a hot topic because it can provide all these advantages. Here we can see in the bottom part of the slide, in the right-hand side, what will be, for illustration purpose, the comparison between the block diagram of a filtering power divider by following the monofunctional approach and the multifunctional approach. We can see that in the monofunctional approach, if we want to create a radio frequency chain that can provide the power division and the filtering capability, the first idea that comes to our mind is to put at the outputs of the power divider 2 filtering units. But the multifunctional approach, what tries to do is to co-integrate inside the own power divider this filtering capability. And by doing that, it's very easy to understand that we will get all the benefits that we have emphasized here, but we will see how we can do it. So after this introduction to the multifunctional philosophy, we will see some examples of multifunctional filtering devices. But in all these devices, we will see that the way in which we incorporate the filtering capability is based off a signal interference approach. Basically, the signal interference approach comes as the extrapolation of traditional digital transversal filtering principles to the radio frequency or microwave domain. So we all know from what we learn in the basic courses of digital signal processing that the conventional way to design a digital transversal filter is to use a multi-path configuration in which what we have is different signal propagation paths that basically, in the most basic approach, these paths can produce some delays or some amplitude weightings over the signal component that they process, and basically we get the overall filtering functionality from the composition of the interference of all the signal components once they have traveled by means of these signal paths. So basically, this is the philosophy that we will extrapolate to the microwave domain in order to incorporate the filtering capability to all the devices that we will see. And the most basic circuit stage that can come to our minds inspired in this multi-path approach will be the use of 2 transmission lines connected in parallel. So basically, we can recognize that indeed this kind of a stage is a signal interference stage because we can see that the input signal indeed is divided between 2 different signal propagation paths that in this case are transmission line segments whose design parameters are the characteristic impedance and the electrical length. And depending on how we select these 4 design parameters, we can obtain a lot of equations for that, but we will not put these equations here. We can get one transfer function or another transfer function. For example, if we want this circuit to provide a dual band response, we need to impose the generation of a constructive interference between the two signal components in the output node at the center frequencies of the two bands. And also, in all the frequencies outside of the bandwidths of the two bands, we want to have a destructive interference in order to produce high rejection levels for unwanted signals. And this is the principle: to force constructive interference in the passband ranges and to force destructive interference in the out-of-band region. Here we can see some examples of filtering components that has been designed by means of this signal interference philosophy. And the benefits that we get is that it's very easy to design multi-band responses with an arbitrary number of transmission bands. Also, to create wide stop bands, that is a problem in radio frequency filters, because in general, due to the frequency periodicity of transmission line elements, it's very usual to have some spurious bands that can allow the resection of unwanted signals. But with this kind of techniques, we can have wide stop bands. Also, the generation of transmission zeros that are very desired to increase the selectivity comes in a natural way, and we have some rejection capabilities. Here we can see two examples of filtering devices based on this kind of philosophy. In the top part, we can see what will be a 3-stage dual band bandpass filter. We put in cascade 3 replicas of the same transversal section in order to increase the rejection levels, but we can easily recognize the transversal section with the 2 signal propagation paths. And we can see here in the comparison between the measurements and the simulations, the transfer function, that indeed we get 2 transmission bands with a very high selectivity. And then in the bottom part, we can see what will be a low-pass filter based on this kind of philosophy. In this case, in order to further increase the rejection level, we have added here 2 steps that allow us to get this benefit. And if we take a look to the S parameters of this kind of filtering device, we can see that indeed for the S21, that will be the transfer function, we get a very high selectivity low pass filter in action, in which we can see that the bandwidth of the rejected band is very broad. So basically, this is the strategy that we will follow to design our multifunctional devices. And the first example that we will show is what will be a Wilkinson type filtering power divider, that is a circuit that is very used in any radio frequency front end. So we know that the classic Wilkinson power divider basically consists of 2 transmission lines and an isolation resistor that we have in the output. By doing that, we can assure a given signal power splitting between the 2 outputs, and by means of the resistor, we are capable to obtain a nice isolation between the 2 outputs. So the idea that we propose here is to replace the transmission line that we have in the classic power divider structure by means of our transversal filtering section that we have presented here, that provides us the filtering capability. So basically, we replace the transmission line by our 2-path transversal filtering section. And by doing that, we will have the power division functionality intrinsic to the power divider schematic, but we will gain the filtering action coming from these transversal filtering sections. So basically, this will be an example of a dual functionality device, because it provides the division capability and the filtering capability. In the bottom part of the slide, we can see what will be a validation of this concept for an equal power division action. That means that the input signal is divided into 2 equal power components in the 2 outputs. And we can see that indeed we have replaced the classic transmission line branches of the divider by our transversal filtering section, in this case for a 4-band transversal filtering section. If we take a look to the transfer function that we get from the input to any of the outputs, we can see that indeed we have the 4-band filtering capability, and inside the passband range of each of the transmission line, we have the power division action. Of course, as we go out in frequencies, we have higher losses, but this is something that is normal. So this is an example of a multifunctional filtering component because provides the power division capability and the 4-band filtering capability. Here we can see how we can apply this kind of filtering power divider to the design of a 2-branch channelized bandpass filtering amplifier. So we know that a channelized amplifier basically consists of, let's say, putting together several branches. And by doing that, we can have a power amplifier that gets some benefits in terms of nonlinearity behavior. So the idea is to add to each of the branches a low order transfer function, the one of these that we have here, that is the transfer function of a low order filtering device, and we replace the classic power divider and power combiner by our new filtering power divider and filtering power combiner. By doing that, we can see that this is the signal interference action that takes place in these two components, and the overall transfer function is this one, that is a very high selectivity one. In the isolation stage is where we put the amplifiers, because an amplifier at the end is a unidirectional device, at least from the ideal point of view. So basically, can add as an isolation stage. So in the bottom part of the slide, we can see the validation of this concept. And here we can see the measurements of this kind of device. So we can see that the overall transfer function is the one of a filter with a very nice selectivity. We have power gain that comes from the active isolation stages that we have here. And if we compare the selectivity of the overall device with the selectivity of the low order filters that we have here, it's very clear that we have increased a lot the performance in this device. We can also apply this kind of philosophy to design of the other kind of multifunctional filtering components. For example, we can think in impedance transformers. Basically, a classic impedance transformer is a circuit that allows us to convert one impedance to another impedance. For example, in order to allow that, a generator provides or delivers all the power. And in microwave frequencies, the conventional approach to do that is to put in cascade several quarter wavelength transmission lines. So the idea to incorporate the filtering capability to this impedance transformer is the same, is to replace some of these transmission line segments by our transversal filtering section. If we do that, we will keep the impedance transformation action intrinsic to this configuration, and also we will add the filtering capability provided by the transversal filtering section. So in the bottom part of the slide, we can see a validation of this concept. In this case, is an impedance transformer that allows us to transform a 25 impedance to a 50 ohms impedance. And we can see that we have replaced the first and third transmission line segments by our two-path transversal filtering section. In this case, it was designed with a dual band filtering capability. So here we can see what will be the input power reflection coefficient, the simulations and the measurements that we have at the input of this device. And we can see that indeed we have a very nice impedance transformation action, because the reflection that we get in these two operational bands is very low. That means that our impedance transformation has been done properly inside the two transmission bands. And if we take a look to the transfer function from the input to the loading impedance, the 25 impedance, we will have something like what is shown by this red curve. That means that we have a dual band filtering response. And then another example of multifunctional filtering device will be one that provides a balance or a differential mode operation. What does it mean? It means that basically, if we think that our signal Basically, a differential filter or a balanced filter is a device that has 2 inputs and 2 outputs. So if we apply a differential excitations in the input that is shaped by 2 single-ended ports, then our device will behave as a bandpass filter. But if we apply a common mode signal that, for example, is the one associated to noise that we want to reject in general, then our device behaves as a bandstop filter. So what we have done is to incorporate our transversal filtering section in this kind of arrangement in order to increase the selectivity that we get for the differential mode action. So in the bottom part of the slide, we can see a validation of this concept. This could be, or this will be the example of a single band balance filter. And indeed, when we apply in the differential input a differential mode signal, that means equal amplitude in the 2 input ports, but different phase with an offset of 180 degrees, then the transfer function is this one, that we can see is the one of a bandpass filter. And here around 2 gigahertz, we will have the operational bandwidth of the filter. But what happens if we apply a common mode signal? That means the same voltage, the same magnitude, and the same phase. Then if we take a look to the transfer function, we can see that now rejects the signal around 2 gigahertz, then the signal is not allowed to transmit. So this will be another example of a multifunctional filtering, because in this case, it behaves in a different way depending if we apply a differential mode signal of a common mode signal. So once we have seen how we can design multifunctional filtering components, another important topic is the design or being able to reconfigure the transfer function of the filter, because this is something that is very desired for next generation wireless transceiver, in order to replace, as we have seen in the introduction, all the static filtering units by a single filtering unit that can handle all the signals as can be reconfigured in center frequency and bandwidth in the transfer function. So basically, reconfiguration is understood in the topic of radio frequency filters as the capability to modify the transfer function in the own device. And this is something that for some basic ways of reconfiguration has been well established during the last years. For example, if we take a look to the literature 20 years ago, one can find already some papers in which is demonstrated how we can control the center frequency of a filter and the bandwidth. In order to control the center frequency, we just need to reconfigure the resonances of the resonators that compose our filter. And this can be done by incorporating variable reactant elements, for example, varactors or trimmer capacitors in the resonators. Bandwidth control is more tricky because in this case, we need to control the inter-resonator couplings. And this is something that was approached later. So today there are several well-known techniques to do that, but we can say that bandwidth control is more critical than frequency control, because frequency control can be done in a very easy way. But what about more challenging designs? That this is something that will be desired for future multifunctional transceiver. And with more challenging designs, we can think, for example, in fully adapted filters that can change the operational mode between a bandpass and a bandstop state. For example, we can also think in fully reconfigurable multiband filters, both to acquire the signals that we want and also to reject a lot of interference that can appear. And going further, we can also think in broadband filters for ultra-wideband receivers that co-integrate the capability to mitigate multiple interference in a dynamic way. So, of course, these are much more challenging design than just controlling the center frequency or the bandwidth in a bandpass filter. So if we start with the first example, that will be the design of a fully adapted filter that can change the mode between a bandpass state if we want to acquire a signal, or a bandstop state if we want our filter to reject an interference, this is a problem that in principle doesn't seem to be very easy to approach, because if we take a look to the conventional configuration of a bandpass filter and a bandstop filter, in this case, this block diagram corresponds to second order realizations, we can see that the configurations are quite different. So the resonators and the impedance inverter that we have are allocated in a very different way. So how we can put together both things? And going further, how we can also make that in all the modes we can reconfigure the frequency and the bandwidth. So basically, following this approach doesn't seem to be the easiest way to approach this problem. So basically, we will see another approach to design a filter that can change between a bandstop and a bandpass mode, and also in which we can control the performances in a very simple way. And the approach that we propose is different from the previous one, and it's the one that we saw here. Basically, what we do is to put in cascade. This is what will be the coupling routing diagram of a filter that in filters is very used, but basically we don't need to have this knowledge. We can just think that what we have here inside the dash box will be like a full transmission path that allow us to transmit the signal at any frequency. So what we do is to incorporate two resonators. For example, if we take a look to one of the stages that we have two resonators that are coupled to this all-pass path by means of impedance inverters. And we can demonstrate that, indeed, by doing that, we can generate a transfer function. We can see that this is in the red box that will correspond to the red dash transfer function that we have here. So basically, we obtain a transfer function in which we incorporate two transmission zeros that corresponds to the resonant frequencies of the two resonators, and we have a passband in between. So if we put in cascade several of these sections, but each of these sections are designed to produce the transmission zeros in different frequency, the overall transfer function is the one that we have here in black, continuous line. That basically is the transfer function corresponding to a bandpass filter with a lot of transmission zeros. But it's very easy to reconfigure the resonant frequencies of these resonators. So basically, if we reconfigure the center frequencies of the resonant frequencies of these resonators, we can easily change from a bandpass operation to a bandstop operation. So in order to do that, we just need to put together the two transmission zeros generated by one of these cells to the center frequency of the passbands of the other cell. So we can see that if we do that, then we suppress the band. So this is a smart way to design a filter that can provide bandpass operation and bandstop operation. And since we can change the performance of the filter by just reconfiguring the transmission zeros, we can get full control in the performance of the transfer function. Here we can see a validation of this concept, in this case, for substrate integrated waveguide technology, in which basically we realize the two resonators by means of integrated cavities, and in order to reconfigure the resonant frequencies, we put some piezoelectric actuators that allow us to reconfigure the resonant frequencies and then the transmission zeros that are generated by each of the cells, and we put in cascade two different cells to have a two-state validation of the previous concept. So here we can see in the left part of the slide what will be the different measurement capabilities that we get for this filter. So we can see how we can reconfigure in center frequency the passband, or for example, we can keep static the center frequency of the passband by just putting closer to the center frequency the transmission zeros, we can change the bandwidth. Also, we can reconfigure the bandwidth just at one of the sides of the passband, and we can keep static the other side. And when we put together the transmission zeros that are generated by one of the cells, we suppress the band. So we pass from a bandpass to a bandstop mode. So this is an example of a highly reconfigurable filter that can behave as a signal acquisition filter in the bandpass mode or as an interference rejection filter in the bandstop mode. So the second kind of designs that we will see is related with multi-band filters, in which we are able to reconfigure all the passbands in center frequency bandwidth and even to combine them in order to control the number of bands that we have active. And there are several approaches that can come to our mind in within how we can design these kind of filters. In order to focus one of them, if someone asks us to design a multi-band filter in which we can reconfigure the center frequency and the bandwidth of the different bands, the first idea that comes to our mind is to put together in a parallel configuration several filtering units that are connected at the input by a wideband signal division block and at the output by a signal combination block. So in this case, indeed, we can obtain a transfer function in which each of the bands will be controlled by each of the filtering units. But as we increase the number of bands that we work from our filter, this doesn't seem to be a very efficient approach, because as the number of bands increase, we need to increase the number of filtering units. Also, the overall bandwidth in which we can create this multi-band transfer function is controlled by the bandwidth of the signal division and the signal combination stages that in the radio frequency domain are not very easy to design. And also the tuning of each filtering unit can affect the other ones. So again, this doesn't seem to be a very efficient approach. So what we propose here in order to achieve these capabilities is to replace single resonant units by multi-resonant units. So basically, we get rid of this previous complex connection in parallel of several single band filtering units by putting in cascade several multi-resonant sections. That means that each of these multi-resonant sections provide by themselves the different passband shaping capabilities. So of course, if we put in cascade several of these multi-band filtering units, we are able to increase the selectivity of the multi-band filtering action. And by controlling the resonators in each of the multi-resonant stages that control each of the bands, we are able to adjust the center frequency, bandwidth, and so on. So this is a more efficient approach because we don't need to duplicate the number of filtering units, and we increase the number of passbands. So here we can see what will be a validation of this concept, in this case in microstrip technology. We use in this case streamer capacitors to change the resonant frequencies of the resonators, and this is a validation for a dual band third order example. So in the top part of the slide, we can see some examples of measured transfer function for different stages of the variable capacitors that allow us to tune the performance of the transfer function. So we can see in the first set of measurements how we can control center frequency and bandwidth of the bands. Here in the red, they are closer, in the black also, but in the blue one, they are more separated. Also, we can keep static one of the transmission bands and we can reconfigure the other band. And even we can control the number of bands that remains active by merging together the two bands. So basically what we have done here is to combine the two bands to shape a wider transmission bands. So at the end, by doing that, we can control the number of bands that are active. And also we can see that we are creating some cross-coupling. That means several transmission paths between the multi-resonant units. We can incorporate transmission zeros that are very designed to increase the capability. Also, we can think on how we can get a multi-bandstop version of the previous circuit, because as we have seen in the beginning, it's very important to have also filters with different rejection or rejected bands in order to suppress several interferences that can appear at the input of the receiver. And we need to take into account that in principle, we don't know the position at which this interference can appear. So we also want that these multiple rejected bands to be reconfigurable in center frequencies in order to position the stop bands at the positions of the interference, but also we want to reconfigure them in bandwidth, because maybe we have an interference signal that has a different bandwidth in one position than the bandwidth of the interference signals that we have in some other positions. And again, if we think in the conventional way to design this kind of flexible multi-stop band filter, the first approach that will come to our mind is to put in cascade several bandstop filtering units, each of them shaping each of the stop bands that we want for our filter. But the problems that we have, in this kind of situation is the same as we have explained it before. If we want to increase the number of stop bands, we need to increase the number of filtering units that we put in cascade. So basically, this means that higher size, then higher loss, because as we increase the number of filtering units in the passband regions, we increase the insertion loss that we will have. So this is a not very efficient approach. So basically what we propose is just to use the bandstop counterpart or the bandstop version of the previous multi-band bandpass filter that we have seen. That basically what we do is to put in cascade several multi-resonant stages, but in this case in a bandstop configuration. So again, what we do is to put in cascade several of these multi-resonant units, but in this case to provide several rejected bands, and by increasing the number of multi-resonant sections that we put, we can increase the rejection levels that we get in the different stop bands. Of course, how we control the center frequency and the bandwidths of the different stop bands is just done by adjusting the resonant frequencies of the resonators that control in each multi-resonant stage the different stop bands. So here we can see in the photograph what will be the validation of this concept. In this case, is a triple band second order realization. So the technology that we use is the same as in the bandpass case. We use microstrip technology with high wavelength resonators, and we control the resonant frequencies by means of trimmer capacitors that allow us to control the positions of the bands, the rejected bands that we generate. In the right-hand side of the slides, we can see some examples about the measured tuning capabilities of this kind of device. In the first set of measured response, we can see how we can control the center frequencies of the different bands that we have. So we have the red transfer function for one case, and then we have some other examples. Also, we can see how we can control the bandwidth of the stop bands, in this case, by making variable the couplings that we have between the resonators and the main transmission path. That we do also by means of trimmer capacitors. Basically, these trimmer capacitors that we have here, close to the direct transmission lines, allow us to control the level of coupling of the resonators to the main transmission path. And by doing that, we can demonstrate that we control the bandwidth of the generated stop bands. And also we can see how we can merge together the different stop bands to control the number of active bands that we have. So this is a good example of a fully reconfigurable filter, in this case with 3 stop bands that can be reconfigured in center frequency and bandwidth. And as the final example about advanced filtering devices with high levels of reconfigurable in the transfer function, we all know that today ultra-wideband communications is a very popular topic. But since in principle these kind of systems need to handle very large or very wide portions of the spectrum, it's very usual that we can get interference signals in such a broad bandwidth. So basically, the idea of co-integrating along with the wideband bandpass filter of our ultra-wideband receiver some controllable multi-band stop bands is very desired, because in that way we will have a unique filtering component that can provide the ultra-wideband acquisition of the overall wideband range of our receiver and having the capability to reject some interference that can appear inside the bandwidth of our receiver. And in this case, the idea that is proposed to design this kind of ultra-wideband filter with co-integrated rejected bands to suppress interference relies on the signal interference philosophy that we have seen in the first part devoted to multifunctional components. So basically, we know that if we put together two in parallel transmission line paths, we are capable to create the response of a wideband filter. This is something that we have seen in the first part of this presentation. So the idea is to add a third path that can provide a destructive interference with the first part inside the operational bandwidth of the transfer function of the two first transmission line paths. So basically, the overall transfer function that we get is the combination of the transfer function that comes from paths 1 and 2, that is an ultra-wideband response, and paths 1 and 3, that is the response of an stop band. And if we make reconfigurable the resonator that we put in this third part, we are capable to reconfigure the center frequency of this stop band. So basically, the overall transfer function that we get is this one. We have co-integrate inside the overall passband of our device a reconfigurable stop band. And we can think in an approach in which we put in cascade several transversal filtering sections. So by each of them, we can incorporate one additional notch. So at the end, we can have an overall transfer function that has the aspect of the one of a wideband bandpass filter, but in which we have co-integrated several stop bands that can be reconfigured in center frequency in order to reject several interference, or even they can be put together to reject a single wider band interference signal. So here we can see the validation of this concept, in this case for a two-stage validation or a two-stage prototype. We can see these two paths that corresponds to the ultra-wideband filter in action, and the third path that we have aided in order to produce the notch. So as we are putting in cascade two transversal filtering sections, we can incorporate two notches inside the wide bandwidth of the overall circuit to reject two interference signals. Here we can see what will be the overall transfer function. The S21 is the transfer function. The S11 is the reflection of the power that we have at the input. And indeed, we can see that we have the wideband bandpass response that comes from the two first transmission line paths of the transversal filtering section, but we have co-integrated two rejected bands very narrow to suppress some interference that can appear. And as we are capable to reconfigure the resonant frequencies of the resonators of this third path, we are capable to reconfigure the center frequency of the notches that we have inside the overall wideband transmission range. So by doing that, we have a circuit that can acquire the ultra-wideband bandwidth, but at the same time has the capability to reject some in-band interference that can appear. So as the summary of this presentation, we have seen that indeed for future wireless communication systems, it's very important to have highly versatile filtering units in which we are able to combine different functionalities in the same device, and also we are able to reconfigure the transfer function of the filtering capability, both from the acquisition viewpoint of the desired signal, but also from the interference mitigation viewpoint. Then we have seen several examples of multifunctional radio frequency filtering components that co-integrate the filtering capability with other functionalities. For example, power division, impedance transformation, and differential mode operation. And all these examples has introduced the filtering capability by means of the signal interference approach that allow us to create in a very easy way several transmission bands and with transmission zeros to increase the rejection levels in the stop band regions. And then in the last part, we have seen some very challenging examples of highly advanced reconfigurable filtering devices with very sophisticated levels of tuning in the transfer function. First, we have seen a device in which we can change between a bandpass and a bandstop operational mode, and also we can reconfigure each mode in center frequency and bandwidth. We have seen 2 examples of multi-band filtering components for the bandpass case and the bandstop case, in which we can also reconfigure the center frequency, the bandwidths, and even to combine the different bands together to control the number of them that remains active. And finally, we have seen an example of an ultra-wave and filtering devices in which we can co-integrate tunable notches to suppress different interference that can happen. So finally, I would like to acknowledge all these individuals with which I have cooperated during this year, because all the results that have been shown in this presentation has been in cooperation with Professor Dimitros Sikoyou, Professor Dimitros Perouli, and Dr. Andrew Gadget. And also would like to acknowledge all the PhD students and local operators, as well as the support from the University of Alcalá, the Community of Madrid, and also the Spanish Ministry, by means of the funding that they have been providing during this year. So thank you very much for your attention. If you have any question, I will be very happy to reply.
Thank you, Professor Roberto. A very nice talk, very interesting. Really, this point of view of from the passive filters, right? Passive filters, yes. to solve to mitigate interferences is very, very interesting. Good point is that well, we are so worried about power consumption at this moment, right? So this is a good solution when we look at that. Mm-hmm. But I can see, of course, a very huge application for this. And when we come to base stations and big systems, but can you comment on how can we like reduce the size of the filters and maybe use that even in mobile applications?
Yeah, this is a good question, because it is true that all the examples that we have seen here are in planar technologies like microstrip, and also in substrate integrate waveguide technologies. So these are technologies that cannot be used or cannot be integrated, let's say, for example, in our mobile. But of course, all these concepts can be also applied to integrated technologies. And this is something that we are approaching now, because at the end, we want to co-integrate all these concepts, or to validate all these concepts in some technologies that can be used, for example, in mobiles. And in order to do that, we need to go to, let's say, passive integrated technologies, in which we can face some problems, for example, the losses, because this is a problem that, in general, when you try to co-integrate or to realize a passive resonator in integrated technologies, the quality factor gets reduced. So at the end, you need to mix together these kind of technologies with some active elements if you want to compensate for loss. But indeed, this is something that we are approaching now, how we can extrapolate all these concepts that can be easily validated in our laboratories in the universities in this kind of technologies to some other technologies that can be more easily translated to the industry, the mobile communications industry. So indeed, this is a technological problem that we are now facing. But let's say that all the concepts that we have introduced here can be applied to any technology. So it's then a question of how good are the performance that you get. And in that sense, a lot of effort needs to be done from the material of the technological viewpoint. But from the conceptual viewpoint, all these principles can be extrapolated to any technology.
Yeah, that's true. That's true. And it is very, very interesting when you look at the limitations that we have in the IC design industry, for instance, in terms of that. Yeah. But of course, these concepts can be used there, and I was really thinking on how to put that in my IC design, right? So it is really, really interesting. Another question that came to me was we are working with this filter, programmable filter, and back in the beginning of software-defined radio, right? We think that we have one transceiver, and we could tune that to solve several problems and several standards and all this kind of thing. But going back again to the mobile application, right? Nowadays we see that this is not useful. We actually need several transceivers at the same time working.
Yeah.
Right. And we do need, of course, all of them depend on very good, high quality external filters because of the interference that we have on the mobiles, right? So this is a tough question now.
Yeah.
And now we have another solution to solve this issue. Even when we look at the base station, right? We can think of smart antennas. That is, instead of blocking the interferer, we can just laser beam the target and reduce that, right? So can you see integration of these two technologies to improve the problem, the solution?
With antennas, you mean?
Yeah, with smart antennas, yeah.
Yeah, let's say that indeed, here in this presentation, I didn't show any example, but another topic that we are facing now is the co-integration of these filtering capabilities with antennas, so that you can also, because for example, how you can create these tunable notches, at the end, an antenna to some extent can be treated like a resonator, because at the end, if you see this one of an antenna, let's say in the it's a frequency selected component, so at the end can be treated as a resonator. So by taking this in mind, we are now trying to extrapolate some of these concepts, especially the one of the multi-interference suppression by means of creating notches, adaptive notches inside the own antenna. This is something that we are facing. And we want to go beyond that by making even these notches to be power dependent, in the sense that, because for example, maybe I know that my system will receive, if it's the signal that I want to receive, the power maybe is this one. But if I receive a signal with very high power, very likely it's an interference. So how you can make this notch to be created inside the antenna depending on the power level? So you need to make this notch to be power dependent. So we are facing now all this together to provide like a very unique multifunctional antenna components that can co-integrate the antenna capability, the interference suppression capability, but beyond that, this interference suppression capability to depend on the power, to have some kind of smart behavior. But in this is a tricky problem because the problem of interference is difficult to handle. And also the reconfiguration, because if one goes to the literature, you find a lot of papers about reconfigurable filters, but how you can do the reconfiguration process in an automatic way? This is a very tricky problem, and maybe this is one of the bottlenecks that is making this technology not to be found today in commercial applications. Because at the end, okay, we can do a lot of prototypes in which we can touch the variable reactant elements and we can show a lot of transfer function, but how you can do in a smart way this? So now there are several approaches like deep learning based approaches in order to be able to reconfigure the filter in an autonomous way by itself. So this is now a very hot topic. And at the end, the success of this subject will determine also the success of the transfer of these concepts to the industry, in my opinion.
Yeah, this that you mentioned is very tough, right? I mean, how can you know which is interference that you want to avoid, right?
Yeah.
Because when you receive the interference, it usually would just destroy the sensitivity of the receiver, and then you know that is there, but you cannot see where it is, right? So
yeah, maybe okay, maybe your system, you know that the signals that you want to receive has a specific type of modulation. So if you receive something that is not in this modulation, probably is an interference. So this is why also some other filtering devices that are now being developed are, let's say, sensitive in the operation to the modulation of the signal. So this is another thing. But of course, at the beginning, you read the signal. Then, with some intelligence, you can make your system to be readapted to, let's say, mitigate the signal. But indeed, there is some information that you need to get from the signal. Maybe the power, the kind of modulation, because if you know that is the signal that you want has a specific type of modulation. But at the end, I think that deep learning and this kind of new approaches, artificial intelligence and so on, they have a lot to say in this problem. So I think that is a very exciting topic, but because can put together two domains that in principle were separated, like the microwave circuit design with signal processing, artificial intelligence, deep learning, and so on.
Yeah, this is tough, especially when you want to touch the wideband systems as well, right? Because if you have the wideband system, it can saturate the receiver also. And then it gets really complicated. We have one question from the audience here from Ricardo, which is, have you integrated some of this proof of concept in recent technology nodes?
Yeah.
Which are the nodes you are targeting?
Sorry, which are the?
Which are the technology nodes that you are targeting, for instance?
Now I am cooperating with one researcher in Australia that is a specialist in passive integrated technology in silicon germanium. And we have started by co-integrating some of these signal interference filters. So the next step is to incorporate the multifunctional capability. So we published like a few months ago an example of a bandstop filter or reflectionless bandstop filter to mitigate interference in a passive integrated technology, even in the millimeter wave range. And the performance that we get are quite good. This was published in the Electronic Devices Letter of IEEE. But this is a very preliminary work because we started this cooperation like recently, and we want to start to incorporate tuning capabilities and multifunctional capabilities to these devices. So hopefully in silicon germanium technology, we will be able to show some results about the extrapolation of these principles maybe in 1-2 years, I guess, if all goes well. But indeed, this is the next step because at the end, all these concepts has more value if you are able to integrate them, for sure, from the industrial viewpoint.
Yeah, I like that transversal filtering session, right? Do you think we can use like maybe not only passive filters, but thinking about integration, like using active filters using the same principle?
Yeah, in fact, this has been already, in fact, I started with what is called the channelized filter. The channelized filter is like a generalization of the classic transversal filter, in which what you do is to incorporate active stages in order to have also gain, and also you make the paths to be frequency selective. So if you do that, you can get even more advanced transfer function. And indeed, these kind of principles can be easily extrapolated to the integrated domain because it's very easy to make integrated amplifiers and so on. There are a lot of solutions for that. And the transmission lines can be replaced by other kind of phase delay circuits, because at the end, the transmission line in these circuits, they play the role of phase delays with some additional capabilities. But of course, if we go to an integrated solution, maybe I wouldn't think in integrating transmission lines, but using other kinds of phase shifters with these active elements to have some transmission gate that can compensate the loss that in integrated technologies are a big problem.
Yeah, well, we've seen some works in the late 20 years, I guess, 10, 20 years, that are I think it started from 20 university, when they started like using this different paths to cancel noise, right?
Oh, okay.
So that's basically the same idea. Like you have two different paths, and you have two amplifiers, for instance, with different profiles, right? And in the end, you add both signals, right? So
okay.
Yeah,
so I think that maybe is familiar. Yeah, from 20, from Brad Nauta, maybe, Professor Nauta? Yeah. I think that I remember now. Yeah, it's true. So I will take a look to this work.
Yeah, it is interesting. I'm not sure they did that actually with passive components, right? But with active filters, they have used that. But they just explored this simple two paths thing, right? I mean, we have many other possibilities to test as well, right? Okay, so well, that is really nice indeed. I'm looking from the inside part of the ship, right? And you're looking at this moment at the outside, and you want to get inside as well, right? So it is really interesting. I think we all learn different approaches for that, right? It's very good for us as system designers, for instance, right, to know what is available at this moment, right? So with that, I don't see more questions here. I would like to thank you very much for this insightful presentation, I would say. And would you like to make some additional comments before I hand over to Professor Hayes?
Well, I just would like to thank you both again for this very nice invitation, because it has been a real pleasure to be here. And despite the difficult times that we are facing, to have these opportunities to give talks is something very nice, because in some way allow us to keep in touch. That is very important. Thank you very much.
Thank you very much. Thank you for this. And now I hand over to Professor Hayes.
So thank you very much again to all, and see you next Friday.
Thank you.
Have a good weekend.
Thank you.
Thank you. Bye.